Good morning. In my presentation, I would like to give you a different perspective about DNA data storage, because in fact, my domain of expertise is more in long-term data archiving. I have been doing that for more than 10 years now. And so for me, DNA is not so much important for the density, but rather for the non-obsolescence and also for energy efficiency. I'm doing this work in the context of the DNAMIC project, which is a project within the Pathfinder program. So here you can see the different partners. We have a wide variety of competencies in this network. Concerning myself, I'm more from the IT field, and I work specifically on the CODEC, in fact. So this is summarizing the concept of this. We are looking for a solution, end-to-end solution for data, for DNA data storage, and we organized this concept around what we call a microfactory, which is represented here. Initially, it is a concept which is used for the watch industry, because I'm come from Switzerland, and so watch is very important. And a friend of mine has developed this concept of a very compact microfactory for making watches, and asked him if we could apply this concept to DNA, and he was very keen to go ahead with this idea, and this is why we launched this European project, in fact. So today I will speak not on all modules, because, for instance, storage on physical archive is not yet done. We didn't already choose a solution for that, but I will speak about the software part, which is within the context of OLOS. I will also say a few words about it. And we have currently two wet bench which are functional for this end-to-end solution. Okay. So, as I told you before, I'm from the field of long-term archiving, and in this field we are using intensely this ISO standard, also called OAIS, for Open Archival Information System. And the actor of this system are the producer, the consumer, and management. So if we look more inside this system, what we find are three modules: the ingest with the submission information package. We have the access module with the dissemination information package. And the most important for us today is the archival information package here. And on top of that, you have two modules, which are preservation planning, where you do some curation, because formats are changing over time, so you have to adapt, and also a part for administration. So what we did this last year, we developed this system, but of course now what we are interested in is to add DNA within this archival information package. So what are the key features of this standard? First of all, of course, you have what we call content information, which is the actual data you want to archive. Could be a file, could be anything. Then you have what we call preservation description information. It gives information about the provenance of the data. We also calculate checksum for ensuring fixity of this data. And we also, very importantly, we usually describe the context of this data, how they could be used, and for whom. And even more important, I think for us, is representation information, where you have to describe many other things. And for instance, you have to describe the decoding parameter of the codec, so that within hundreds of years, you are still able to decode your DNA. And also, you can add the software tools and other things like emulator. I will speak a little bit about it. And why doing that? Actually, it's because the OAIS standard asks for self-description principle. Normally, your archive should be self-described. So if you lose all the computer system around it, at some point, you should be able to retrieve your information. Usually, self-description is done within what we call a designated community, but this is a little fuzzy because in 100 of years, not sure this community is still existing, so we try to be even more general than that. And also what we try to do is to be able to recover in case of disaster. And this is based on representation information, where you are supposed to have everything needed to rebuild your system. So self-description is a notion which depends on two things. First, the complexity of describing your system. You should be able to describe your system as much as possible to be able to then interpreting your system. Both are related, actually. And for DNA, for instance, you should be able to describe your codec, and it should be the less complex as possible, because a complex codec will need more information to describe it, and also more information to interpret it as well. Either you use a compact description within DNA, that's a possibility, you encode everything in DNA, or you use another material, for instance, microfilm, or just paper. In the nuclear industry, they use intensively the paper for some part of the description in this OAIS standard. So, of course, the goal is to be able, for the future generation, to be able to decode DNA. We can also give some measure of complexity. There are some metrics for that, for instance, Kolmogorov complexity. And at the end of the day, in fact, you have to design a universal Turing machine, and also you have to be able to define a simple emulator. So you rewrite your codec in a simpler language, so that in the future, computer engineer will be able to rewrite an emulator which is going to replicate your codec. So 7 years ago, we developed this system, which is used. So it's sold under the OLOS.swiss trademark. It is used nationally over all Switzerland for the researchers. They can use this system to archive for the long term their research. And we designed this system to be very modular with submission information package, dissemination information package, and of course, the archival information package, which is the most important part for us. Today we use file storage and tape storage, but within the context of DNAMIC project, we are developing this connector to go to DNA through the microfactory. This is to show the structure of archival information package, which are zip files. So we are completely agnostic to the format. We use bits. And if we look inside the zip file, you see that a lot of information is metadata. Actually, we have a lot of small files for tracing every operation you have done on data. And for instance, you see this is an image which is within this folder, and around it you have a lot of metadata. So when you want to translate that into DNA, you have your codec, but also you have this representation information which can use another codec, for instance, maybe a simpler codec, or another way to save this very important information. So now I just describe shortly the other two workbench which have been implemented for DNAMIC project. So one is for DNA amplification, and also we do some concentration measurement. So this shows the device which has been implemented for automatizing this process. For the workbench 2, we use, it's based on OpenTron, and we have the primer synthesis within the system, and we have DNA library preparation, and also, again, concentration measurement. So what we adapted is the thermal unit and filtration unit for PCR, and also we integrated Oxford nanopore minion to, we see it here, so that a robotic arm can go and put with micropipettes the DNA. Because in this consortium we work with Genomica, we also benefited from a new wet lab protocol, which is very efficient for nanopore. It uses less reagent and is very good quality. And this really, I think, improves the success of decoding DNA. Finally, we should not forget that for all the system to work, we need a supervisor system, which is quite complex, and which has been designed even before for watch industry, but we adapted it for DNA. So just to show you a concrete example, for here, for instance, we want to retrieve information. So from the OLOS platform, by the way, I didn't say, but OLOS is completely open source, so it's available to any user. And so we have the different state diagram to control the microfactory. But what I wanted to show you here is that given a certain criteria, for instance, the number of based on clustering of the strands, we can, at some point, we can stop sequencing. So we also we avoid to use too much reagent for the sequencer. So this is a retroactive feedback we can have given some criterion. So we can stop sequencing at some point. So concretely, what we did, for the end-to-end, what is represented in green has been tested. For now, it's semi-manual, it's semi-automatic, so some parts are automatic, some parts are still manual. But the important thing is that we could encode from this OLOS system based on OAIS. We could encode the information to DNA. Of course, we are not yet ready to synthesize a lot of quantity, so we ask Twist to synthesize the DNA. But then the primary synthesis is within the microfactory. And so all these steps have been done by the machine. And at the end, I can show you, we tested six use cases. So for a total of over 7 million of nucleotides, and we could decode without any error because, as I said before, we use checksum for the fixity of information, and even one bit error could compromise the file, actually. So what are the challenges, the next step? First, synthesis is currently limited to primers, so we would like to be able also to synthesize everything. Waste management is a problem within an automatic system because at some point you have to intervene to change some material, and we would like to minimize this kind of handling. For disaster recovery, we have ideas, but it has not been yet implemented. And also we are working now very hard for optimizing the codec so that we can target the terabyte scale in terms of computing time. And finally, I would like to thank all the team working in the DNAMIC project. Thank you for your attention.
Do we have any questions? On again.
With the end-to-end system you're showing, the throughput is rather very limited. So, and you mentioned eco-acoustic other systems, but this would also be limited in terms of throughput. So do you have a view how this could evolve in terms of parallelization instead of 96 pipetting in parallel? Imagine something that will future versions that would improve in terms of parallelization and throughput.
Okay. In fact, for the megabyte scales that we are dealing with now, the throughput, I mean, the computing time is the order of 30 seconds, so we can stop sequencing after 30 seconds. So already we have some part of parallelisms at the output of the sequencer, but we also are working for parallelizing all the codec steps, and we are working with FPGAs and GPUs.
Any other questions? I had one. So right now when you're synthesizing your primers, you're doing that with peptides?
Sorry, so the primers?
It's
yes.
done on CPGs and phosphoramidites?
Yes.
Okay.
Yes.
So just sort of standard old school synthetic biology that way.
Yeah, we are using the Kilobaser system.
Okay.
From Austria.
Okay. Any more questions? Okay, well, then we'll move on to our next presentation, which is going to be an online presentation by Olivier from BioMemory. And it's, oh, thank you, everyone.